Okay, in Unit 5, we're going to be looking at neural networks. I'm really excited about neural networks. I did my PhD research in neural networks. We're going to spend 2 units on neural networks. This unit just covers the basics of neural networks. And then next unit, we're going to look at more advanced neural networks and something called deep learning. Today, some of the best neural network or best AI methods and solutions are being done with advanced neural networks and deep learning. So we'll spend a whole unit next week covering those. But to prep for that and to really understand those, we need to do some basics. So we need to understand what a basic neural network is, what are the nodes in the neural network, how do they compute inputs and outputs, how do we structure them together in networks, and how does learning happen. And we'll look at something called backpropagation for learning. So let's start by looking at these resources for neural networks. So start with by looking at these 2 short YouTube videos on neural networks. They're from Georgia Tech's machine learning course in Audacity. This is a really nice course. I really enjoyed. It's a free course on Audacity. So if you are very interested in machine learning, including what we did last week and some more stuff, I'd suggest that. But here, just watch these first
Hey
videos.
Charles, how's it going?
It's going pretty well, Michael. How are things going with you?
Good.
So Charles and Michael are 2 faculty there, and they go over. This is just a 3-minute introduction to neural networks. Talks about what a network looks like, and then breaks it into a mathematical function. Um, Neural networks are relatively simple math, so go through this and see. One thing you will see that you may not have seen too much is the sigmoid symbol. This says to sum up a bunch of values. For coders, I often translate this into a for loop. This is basically says for I equals 1, I less than k, and then calculate this term and sum them all up. So we'll sum up x sub 1 plus w sub 1 plus, and then we'll add that to x2 times w2, and we'll add that to x3. And so it's just a loop that goes through that. So that's a symbol you may not be familiar with. They'll talk about this basic stuff in original perceptrons, where this was a linear function that did this calculation here, and we calculated sometimes just an output of either yes or no, 0 or 1, or just some linear value from these inputs. And basically, you'll see here, we're just taking a set of inputs, multiplying it by a set of weights to get some total here, and we apply some function to that that calculates our output, and we send that to the next nodes in our network. So look through this, and then go on to this next thing. Now, neural networks have a long history. They've actually been around for quite a while. In the 40s and 50s, we came up with this perceptron model of networks, and a lot of people were very excited about it. And we started doing some simple networks. But one thing you'll find in artificial intelligence and computer research is that interest in research kind of sways back and forth, and a couple key people can often dictate the future of some of this research. So in the 50s, 1 or 2 researchers came out with this problem that where we just have 2 layers of these neural networks, and they could not solve simple problems. One was what is called the XOR problem. So in that problem, you're trying to classify, let's say we're trying to classify movies as good or bad movies, and you knew that they were either had action or romance in them. And so good movies either had, let's say, action or romance in them, but not both or not neither. The system could not solve even that simple classification problem called the XOR problem. And there are other issues that said that with these linear units, if you have multiple layers, you can reduce them all to a single layer. And so that kind of threw a wrench into that research, and so it was dropped for many years. One couldn't get funding. Had researchers, the government would not fund research on it because it was thought of a dead end. Then psychology developed a number of research areas and eventually kind of developed their own neural networks. And this came to the forefront by the time I was in grad school. I still have here on my desk, I grabbed at the original parallel distributed processing by Rumhut and McClellan. This is a textbook put out in 1986, or just a set of papers about their neural networks and setting those up. And this really kickstarted the neural networks again in the 80s and early 90s. And we created what we're looking now. And that's what you'll see here in this second video here, the three-layer network using back propagation to train it, and that's what we'll be doing this thing. And in the 80s, we thought this was going to be a great way, and we did a lot of stuff. But come in the mid 90s, again, we were running into some stumbling blocks, and there were again some people saying this just isn't working. We had this problem where we couldn't learn significant things, we couldn't set up networks with more than three layers, and so funding again fell away when we had some key researchers saying that this was really a dead end. And so again, this faded away for 15 years, 20 years. And then just in the last 5 years, it's really come back. A number of researchers have developed techniques for deep learning, and it has just really grown. And so we'll look at that in the next unit. So, but this unit will talk about this three-layer network. So watch these intro videos, and then go to one of these videos tutorials. So I'm just going to click on this first one. This is a quick neural network tutorial by a site called AI Junkie that tries to do neural networks in plain English. One of the challenges sometimes we have with this is neural networks do use a fair amount of math, including calculus for derivatives, and linear algebra stuff. It's sometimes challenging to find explanations that do not require that much math. But this talks about, again, the basic neuron that we're trying to model. And one of the things we look at is how to model this, how much detail to model this in. The actual neurons are very complicated. They have actually different ion channels for collecting different types of connection synapses to other neurons. There's a whole different types of those. They have different ways, pathways with different ion channels through the neuron and out, and they calculate things, and the calculations of how they send out the output is complicated, and it's unknown what of all this is needed. And so we try to do different simulations of this. So we just try to work on the key features to create a simplified version of the neuron. But one thing like a simplification we often do is that neuron are always firing. It's firing, 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 and then if it gets a bunch of out inputs, it'll fire more, fire, 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 and then it'll go to. So the rate of firing is down of electricity down this axon dictates this, and we just approximate that. We often at some of these things, some models, the models we're going to look at, do not model every firing of the neuron, but actually just model a number for how frequent we're firing. So we'll have, if this is very active and firing a lot, we'll say its activity is 1. If it's firing very little, we'll put the activity at 0. Okay, so again, main idea is we have a better set of inputs from other neurons. Each of these inputs has a weight. In our neurons, we have a connection from one neuron to another. The synapse has an efficiency, and so much electricity will go that. And these weights become key as these weights will change as we learn things. So if we learn an association between this and this weight will strengthen. And then, like when we hear part of a song, we will, through these weights, remember and recall more of the songs, or any sort of memory like that, or calculation. Now, the output can be binary. We can just calculate the inputs, and if the input is above some threshold, we can just output either 0 or 1. Now, more commonly today, we have an output that is, let me get to the next one. Is continuous here, where depending on how much input we have, we'll calculate some output. So if we have lots of input, we'll output 1. If we have very little input or negative input, we'll have zero output, and then it's a curve between that. Sometimes, again, our weights can be positive or negative. Sometimes they're all positive, depending. There's lots of different neural network structures we will try out. So again, the calculations for this, if we're trying to figure out the how much we sum up all the inputs going into this neuron. We're going to sum up, and each one we're going to calculate the input times its weight plus the next input times its weight. And so we write this equation mathematically with this sigma function, but you can also think of it as a loop where we just loop through all the connections. We have an array of values here, we have an array of weights, and we loop through, and each one we multiply the input by the weight and sum those all up. And so again, here's the loop version of this calculation. So we have these neurons, and so we group these into layers. We generally work with 3 layers. We have a set of inputs that we will set with our data. We have a set of hidden layers. Each hidden layer is connected to every input here. And we have a set of output layers, and this is what we're looking at for our results. This is called a feed-forward network because all the weights are going forward from inputs to outputs. Later on, we'll talk a little bit about recursive networks and other network structures. But this is the most typical, or it was in the 80s and 90s, and is still used a lot today. And it's fully connected layer. So the output layer, one neuron node here is connected to every of the hidden nodes, and each hidden node is connected to every one of the input nodes. So we might take, and we'll look at this pixel image like this, and so we'll take the pixels as maybe either on or off, or a shade of gray between 1 and 22 different things. Now this is 8 by 8, so there's 64 units, so this would result in 64 input units. And then maybe we're going to try to categorize these digits as a number between 1 and 10, or 0 to 9. So maybe we'll have 9 output units, and we'll look at a simulation of this sort of pattern in a little bit when we get to our simulations. This is another thing we're not going to talk about this simulation, but here's our sigmoid function. There are a couple ways of doing this. So if we sum up all of our activation, how do we then compute our actual output? It's important often to have some sort of non-linear curve here that really helps with the computation of things. And so one of these is called the sigmoid function, and it's this function here. Another one is an arctangent function, which is similar in complexity. But it's not that important that you know this function, just know what it does, and that it is the more activations we're getting, the more activation coming into a neural net a node, the more output is, but it's a nonlinear curve. So, then this walks through some code with this. I'm not going to walk through the code for this in this tutorial, so I'm going to just quit this here. Okay, so again, read through either this tutorial or that tutorial, one of these, and then we're going to try out a couple simulations to talk to you about things. So let's run this first simulation of a basic network. So you can just say build your own network, and it'll start with a basic network. Just hit build. So you can do more complicated networks, but this is the basic one. So here's our network. If you go over the nodes, it'll show you what's connected. So here our output node is connected to our 3 hidden nodes. And this hidden node is connected to our 2 hidden input nodes. So you can kind of see the connections. Every connection will have a weight associated with it. And they start at some random values. So we started a bunch of random values here. And now we're going to learn some things. So I'm going to run this a little bit. And so the first thing is it's going to calculate this node up here, and then this node and this node. So it's going to calculate this node by, so right now our inputs is, this one's going to be active a 1, and this will be inactive as a 0. So we're going to run this. It's going to update this, calculate that value. It's going to update this and calculate the value here. And so again, all we're doing is taking this 1 times this weight and adding it to this 0 times this weight to get this 0.143. And then again, once we have that sum, we do some sort of sigmoid function on that. So we update this one, and then once we've got all these updated, we can update our output unit. And again, this is a really simple program with only one output unit, but we may have more in another bigger unit. Now, let's talk about training and something called backpropagation. So we'll do supervised training. We'll know some inputs and the output that we want the network to learn. For example, in our course, in our activity later on, we'll be looking at breast cancer data. So we'll look at some readings, and then we know whether or not that's breast cancer or not. We can train it. We can put in some readings, some inputs, and say this should be breast cancer. So we want this particular output here. And now we want to train our network to learn that. And so what we're going to do is modify these weights. So we know what it should be and we know what it is. We can figure out the difference and we can propagate that difference back here, or and update these weights. So again, when we run this, the red is the updating of the weights as we go through. So we update all the weights, and now we go here again and we run this and do a new calculation. We calculate that, and this, and now we're going to propagate that weight back. So you can kind of watch these weights, and as I run it again, these weights will change slightly. You see them change quickly, and now we'll go back here and we'll change these weights. And back propagation is a way of taking this error that we have here and propagating back and figuring out what this hidden node should probably be and propagating that node back. So we can update all these weights, and then we can go forward again and up and calculate these values. Now there's lots of ways of doing this and optimizing this, but that's the basic idea, is that we know some inputs and an output, and so we have our data we train the network on that we go through. So that's just the basics of this neural network, and you can actually try this out. You can set up more complicated neural networks here, but I'm going to go on to a different simulation. Let's look at this simulation. I'm going to reduce the number of hidden units to 15 here to make this a little faster. And we're going to do some pattern recognition here. So this is a neural network where we'll have a set of digits here, like 3 or 4, that we'll put into this. Now this is just a 3 by 5 grid, and they're either off or on, so we have 15 inputs. So this pixel will correspond to this input, this pixel will correspond to this input. So they've just mapped these pixels to these inputs. And then we have 9 outputs, because we should be able to learn that this is this is a 4, and this is a 9, and this is a 0. So actually we have 10 outputs, 0 through 9. So these are our 10 outputs. Whichever one of these becomes most active so if this one becomes most active, we'll say that's a 0. If this becomes most active, we'll say this is a 1. Okay. And then we have some hidden units here, and you can see each hidden unit is connected to every one of the inputs, and each output unit is connected to every one of the hidden units. And then we're going to train this. So we're going to send a bunch of data in here and train it and update these weights. So I'm going to hit initialize to get some initial random values to all the weights, and then I'm going to start training. So now I can run for a while. Initially it's not very good. I'm going to pause this. It's getting 95% of the values wrong. So I can go down here and see. So like 2, I can say recognize, and it thinks it's a 1. 4, it thinks that's a 4. Well, I got that one right. 6, it thinks it's a 1. 9, it thinks it's a 4. So it's not doing very well at its predictions yet. 95% error rate. So I'm going to resume this and let this calculate. And I'm going to kick this up a little faster. Okay, so now it went fast, and the error rate dropped down to 0.5. And so if and again, it's going to keep running until I get to a certain error rate. And so it stopped when it got to that error rate. So now just 5% of the time it'll get something wrong. So hopefully if I show the network a 1, it will recognize it. If I show it a 2, it'll recognize it. Show it a 4, it'll recognize it. Show it a 7, it'll recognize it. And again, you can see when we put in a 7 here, it it the it's all dark. These are very active, so it has these very active, and then it predicts the outputs. If we actually see, it thinks it's 0.01 chance it's a 1.00, and then actually 0.97. It is really sure that it's a 7 at this point. So again, you can try this training, try to run this network, and see as you go how it learns to classify these values. Okay, so the next network we're going to look at is from Google's Tensorflow. This is actually for deep learning and Google's deep learning environment, but we can use it for simple network stuff also. So start by, let's do this, click on this data input, and we want to delete, we just want one hidden layer here. So let's see how that goes. Now, well, let's do no hidden layers. There, no hidden layers. Now, so we just have a set of inputs, and there's different ways of setting these up, but these are just the way the inputs are set up. And we're trying to classify these dots as one way or the other. And so we just have the inputs feeding into our output, and we can train this. If I go here, it'll train this, and it'll learn this classification pretty well. And without any hidden units in the way this is set up, we really learn a linear line differentiation. We can learn everything on one side of the line is one way, everything on the other side of the line is the other way. But we can't learn more complicated things. So without any hidden layers, if we try to learn a more complicated classification scheme, so I'm going to click on that one and try to run that. Again, it's trying to just learn a linear line here, and it has trouble. It's there's no line it can draw through here that'll differentiate them. So we need to add some hidden layers in here. And again, this is where we were at in the 40s or 50s. We realized that we had problems here, and we stopped doing neural network research for 15 to 20 years. And so then we finally figured out, oh, we can just add another layer here, and as long as we use these sigmoid functions, it makes sense to have another layer here, and then we can train. So now, again, I can still train on this sort of data really quickly, but I can also train on, for example, this kind of data. So it's trying to learn these methods here. I'm going to add maybe some more hidden units so it can do some more learning here. Let's try this again. So if I stop this, reset it, and I'm going to, if you add, let's say, 5 hidden units, I can do a little better computation here. And then if I run this, it can quickly learn to classify this sort of stuff. And you can kind of, I don't know, you can play with how this is classifying, but it's not that important. So now we have these hidden layers, and we can classify this data relatively quickly. And what we'll see when we get to next unit with deep learning is we'll add multiple layers. We'll add more layers to this to learn more complicated things. So you can actually try to see how it'll learn if your setup can learn like this sort of a structure. And again, it's trying to classify these as either orange or blue, and it's having some trouble with some of these with this many neurons. And here's a very challenging classification thing, and so most of these, a 2-layer network will generally fail with this sort of system if we run that. But again, we'll see if we add another hidden layer here and have some more units, we'll be able to learn even these more complicated systems. So, and again, that's more for next unit. We'll be getting into this. Okay, so the last thing I want to do is, we talked a little bit about linear classifying. This is another visualization I wanted to show you. And what this is just simple data, and it just shows how having multiple layers remaps the data in different ways. This is using convolution neural networks in JavaScript, and we'll actually be using this to do more complicated deep neural networks next week. But this just shows our network structure here and how we can take a complicated pattern. So these are units all classified as one area. These are different. And like we looked at k nearest neighbor last week, and this would not work very well with k nearest neighbor because this might cluster, but this cluster is kind of spread out. And so it's a challenging clustering algorithm. Similar with this sort of stuff, this is can be a challenging clustering algorithm. But when we have a multiple, our hidden layer, and it's hard to explain what this visualization is, but the hidden layer kind of remaps the input into a different format so that we can draw a linear line to differentiate this. So although we could not draw a line here, a straight line to differentiate all the reds from the greens, by remapping it into a different set of coordinates and stuff, we can do that. And again, we're looking at different ways, and this is again a very common, very challenging problem where we have this spiral classification. And again, you can kind of see how learning is trying to, the hidden layers is trying to distort this structure. And so eventually, with the right setup, this will learn this classification structure and how to map the data by changing the weights so that it can classify this. Okay, so that's the basics of neural networks for this unit. We're going to look at a different simulator that actually has Java code there that you can run. So in this participation activity, you can watch the video, and we're going to grab some breast cancer data and walk through the simulation here. By Thursday, our department's decided to use Thursdays now as the standard midweek day for everything. So I'm going to have everything midweek due Thursday night by midnight. So you have to go through this participation activity by Thursday at midnight and post the error rates you achieve for your first 5 trials. And then by Sunday, you either have to post a question and answer or your error rates. And then the assignment builds on that. We do part of this tutorial here, and we'll finish up the last part of the tutorial here for your assignment for this week. So that's our introduction to neural networks, and then next week we'll dive deeper into deep learning and deep multi-layer networks.